Every second, the global internet successfully routes billions of packets. Thanks to the IP addressing system, a piece of data can travel thousands of miles and hit its exact destination hardware with near-perfect reliability. But reaching the hardware is only half the equation. Once that packet arrives at the machine, the network layer, Layer 3, has done its job. The data has reached the door, but it lacks any instructions on which specific application it needs to interact with. A single modern server rarely executes just one task. It operates multiple processes concurrently. Behind a single IP address, a machine might run an Apache web server, a database, and an SSH daemon simultaneously. To sort this incoming data and establish end-to-end communication with specific processes, the architecture requires a bridge. This is the responsibility of the transport layer, or Layer 4 of the OSI model. Layer 4 solves process routing using a 16-bit namespace managed by IANA, yielding 65,536 ports. This enables multiplexing, running web and database queries concurrently. This channel is mathematically defined by a five-tuple, source and destination IPs, ports plus protocol, forming a precise socket. Without this strict socket architecture isolating the traffic streams, an incoming web request could easily route directly into a database instance, resulting in catastrophic crosstalk and data corruption. Layer 4 forces an architectural trade-off. To maintain functional integrity across different types of applications, the system must balance the need for guaranteed delivery against the demand for raw speed. For applications that require precise ordering and guaranteed data integrity, the transport layer uses the Transmission Control Protocol, or TCP. This diagram outlines TCP's connection-oriented logic. Before any actual data is sent, it establishes a session through a strict three-way handshake. The client sends a synchronized packet, the server acknowledges it, and the client locks the session with a final acknowledgement. This reliability carries heavy overhead. TCP requires up to a 60-byte header, labels every packet with a sequence number, and relies on an acknowledgement system. If the sender doesn't receive an acknowledgement within a specific time frame, it stops and retransmits the data. The alternative is the User Datagram Protocol, or UDP. It is a connectionless protocol built to eliminate overhead and maximize latency reduction. There is no handshake and no session setup. UDP drops sequence tracking and flow control entirely. Its header is fixed at a minimal 8 bytes, pushing raw data across the network as fast as the physical medium allows. The TCP acknowledgement system introduces a critical flaw for continuous streams: head-of-line blocking. If a single packet is lost, TCP halts the entire data stream to wait for retransmission, causing noticeable delay. For live video feeds, voice over IP, and online gaming, timeliness matters more than perfect integrity. In these real-time streams, ignoring an occasional dropped frame is far better than pausing the entire experience to wait for an acknowledgement. The strict choice between stateful reliability and stateless speed at Layer 4 dictates what the application layer can successfully achieve. Beyond the mechanics of how data moves, the structural namespace itself requires strict governance. The Internet Assigned Numbers Authority manages this registry to prevent network chaos. IANA divides the finite 16-bit namespace into 3 specific categories, each with distinct rules and privilege requirements. The first block, from 0 to 1023, is reserved for well-known system ports. Binding to these ports require root-level administrative privileges and strict IETF registration. It includes foundational protocols like SSH on port 22 and HTTPS on port 443. The registered user ports span from 1024 to 49,151. These are assigned through an expert review process, allowing enterprise software creators to utilize standardized connection points, like port 3306 for a MySQL database, across any enterprise environment without requiring system-level access. Finally, the dynamic ephemeral ports run from 49,152 to 65,535. These are strictly temporary. The operating system assigns them randomly to client-side applications, like your web browser, just long enough to receive return traffic during an active session. Network administrators must know this taxonomy. Any open port operating outside of these conventions indicates a misconfiguration, or worse, an active compromise. Knowing the taxonomy only matters if you can actively observe which ports are listening on a host. Historically, system administrators mapped active connections and internal listeners using netstat. However, netstat is bottlenecked by its architecture. It functions by manually parsing text files stored in the Linux directory, which severely slows down its performance on modern machines. This flowchart illustrates why SS, or socket statistics, has replaced it. SS establishes a direct pathway straight into the core kernel ring, resulting in vastly superior query speeds. When running these tools, administrators must use specific flags, like -key. Identifying an open port is incomplete data. The tool must bind that port to a specific process ID to verify that the underlying service is legitimate. But checking the local kernel only gives you the internal view. You also need to audit the host externally, exactly as an attacker would. For external observability, administrators rely on Nmap. It probes a host's defenses by firing packets across the network and classifying the results into specific strict states. An open state means an application is actively accepting connections. If that application lacks current security patches, it is a direct vulnerability. A closed state means the port is reachable, but no application is listening on the other side. This still provides useful intelligence, confirming the host is online and aiding in OS fingerprinting. A filtered state means a firewall intercepted the probe entirely. Nmap cannot verify if the port is open or closed, indicating a hardened defense. Without internal kernel visibility through SS and external probing via Nmap, an administrator is functionally blind to the true dimensions of their attack surface. These mechanics, taxonomies, and observation tools synthesize into a practical defensive doctrine known as server hardening. The foundation is the default deny principle. A secure firewall drops all inbound traffic. Every exception must be tied to a legitimate business need. For a secure website, the firewall opens an exception for port 443, keeping the perimeter sealed. The highest priority targets for attackers are the administrative interfaces, the management plane, which typically rely on SSH or RDP. Exposing these ports to the open internet invites automated brute force attacks. Administrators secure the management plane by restricting access entirely, ensuring these ports only accept traffic from verified internal jump host subnets. A strong exterior firewall is necessary, but true hardening requires auditing the interior operating system configuration as well. Modern operating systems ship heavily bloated. They run legacy daemons and convenience services by default, meaning they listen on ports that the actual enterprise hardware will never need to use. On Linux machines, administrators actively strip these out using commands like system control stop and disable to kill print servers and internal discovery protocols. In high-security environments, they take the extreme step of masking the service. This breaks the symlink, guaranteeing no rogue secondary process can forcefully spin the service back up. Windows environments require equal diligence. Administrators utilize PowerShell to hunt down and disable the startup types for consumer-focused services, like background Xbox Live processes that waste system resources and create unnecessary attack vectors on enterprise databases. The secure management of the transport layer is an active, continuous requirement. By understanding the math of the namespace, auditing active processes, and rigorously enforcing a default deny posture, administrators ensure the structural integrity of the network.